Good morning. I am Krishna Kumar from Krishna's Classroom. We continue with our discussion on analysis on R. In fact, we were looking at in some depth the structure of R. And we found that the last time we observed that the choice of basis for Rn is not unique. Most of this goes word by word to any linear spaces. Although we often work with the so-called standard basis, namely E1, E2, etc., there's some advantage of doing that. Now, there are situations, it will be clear when we start looking at transformations or linear transformations on Rn, that a particular basis may be more suitable to discuss the problem, or it will give more transparency to the discussion of the problem. Again, we will start looking at it in detail when we go to work on transformations on Rn and their representations in terms of a basis. That's a time when we want to discuss such details. But therefore, how do we choose a basis? As we know, it is a linearly independent set which also spans the whole space. We also know that there exists a basis for Rn. There exists a basis given a set of linearly independent vectors. You can construct a basis which contains in it the given linearly independent set. So all this is possible. Therefore, there is a very definite way of constructing basis. Now what we want to look at, of course, last time we also proved the isomorphism theorem, which said that introducing a basis means defining an isomorphism on R. An isomorphism is a linear one-to-one onto map on R. Okay? So these are synonyms. I said yesterday that to have an isomorphism, then you can determine it, or you can choose a basis which determines it in a particular way. And so also, if you have a basis, then it defines an isomorphism on R. This is the relation between the isomorphism and the choice of the basis. Now what we want to explore is this. Suppose you have two different bases. Okay? How to go from one basis to the other? Okay? Let us start with the assumption that we are working in Rn and we are working in the standard basis. Okay, so all the discussion will be in the premises of the standard basis, namely E1, E2, etc., En. Okay. Now let us first make an observation. Suppose this is a copy of R. Okay. Now denote a vector by x. I don't know how it looks like. Now I can map it to another copy of Rn using the standard basis. What do? I choose the basis E1, E2, En for Rn. Now, what I do is, I write this as x can be written as x1 E1 plus etc. xn, or the vector x can be identified with. Okay, we take this as an ordered basis. Now let me use that word, ordered basis. By which I want to distinguish between E1, E2, etc. En and a permutation of that, a non-trivial permutation of that, because the order will be different. So if you write Ei1 In, where Eij is some Ek, and still this consists of all. So it's just a permutation of that. Suppose if it is a permutation of that, then as a basis there is no difference because both the sets are the same. However, as an ordered basis the two are different, because you are going to say what is the first element, what is the second element, and so on. So with respect to, so we fix the order initially, so we start with an ordered basis. Now once the ordered basis is chosen, then you see that x can be identified with the ordered n-tuple, where xi's are the coefficients that appear in the linear representation of x in terms of the ordered basis E1, E2, etc. En. So I choose this point. Now if you choose y, you also have the corresponding representation. If you have x plus y, then there is these two add up. The image of x plus y under this consideration will be simply the addition of these two vectors and so on. So these things we have discussed. So to see that corresponding to x there is a unique n-tuple, ordered n-tuple, x1, x2, etc. xn, based on the choice of this basis. Okay, so we write this, we denote this map by phi. So phi of x and phi is an isomorph. Now you can do this with any ordered basis. Suppose this is of now you see that any x belonging to Rn can be written as x equal to c1 x1 plus cn xn. Once again, we associate with X is mapped onto the n tuple, ordered n tuple. And one can show that this map is also this is an isomorphism. This is an isomorphism on R. So every choice of an ordered basis for Rn would determine a corresponding isomorphism. Okay? Right? This is the important observation that we make, and this is how the isomorphism is defined. If x is equal to c1 x1 plus c2 cn xn, here you see that c1 c2 etc cn are uniquely determined because x1 x2 etc xn is a basis. Okay, therefore this ordered n tuple is uniquely determined. So corresponding to x, there is a uniquely determined n ordered n tuple with respect to the x1 x2 etc xn. Now one thing that you should observe is that if you were to change this ordered basis into some y1, y2, etc., yn, then you are going to get a different image. As it would have been clear from the consideration that we made in the last lecture of R2. So this is essentially a choice of the coordinate system for the space. So a choice of a basis means we are going to choose a specific coordinate system in which gives you some advantage, so that you carry out your discussion in the framework of that ordered basis, okay, or coordinate system. So it is much more easy to work with a specific coordinate system than quite often with the standard coordinate system, and that will be dictated by the problem. Okay, right. Now you see that this is the isomorphism between Rn and Rn through a change of basis. So we have started with Nx, we have discovered the coefficients that go with the vectors to give the unique representation as a linear combination of x1, x2, etc. That's how you make the isomorphism. Right. Now the question that we want to ask is, you have consider this as an abstract space. I will be denoting a particular vector by some symbol. Okay. So since I want to use x1, x2, etc., xn and y1, y2, etc., yn, I will use z as the arbitrary vector in R. Now I choose an ordered basis x1, x2, etc., xn. So I choose an ordered basis let the corresponding, let phi denote the corresponding isomorphism. So we are identifying the choice with this. Now once you have that, let Z be determined by alpha 1 x1 where alpha i's are uniquely determined. Now I associate with Z is identified with is mapped to alpha 1 alpha n. Let me denote this by alpha. So this belongs to R. Alpha belongs to R. So I have alpha here. This is a copy of R. So what I have is Z is mapped to alpha by phi, and phi is determined by now let me make another copy of R by choosing another ordered basis. So choose then Z is equal to say beta 1 where beta i's are uniquely determined. So beta i's unique. Therefore, I define psi by psi of Z equal to So I get another image for Z defined by psi. Psi is an isomorphism. Both two different isomorphisms. So what I have is psi, which is identified with y1. So this is your beta. So this is an isomorphism, this is also an isomorphism. So 1 to 1, 1 to 1. Therefore, now it is quite easy to see how these two are related. What is this? This you can see that is very simple to understand because you go from here to here. In fact, the path you want to cut out is start from alpha, go to Z and go to beta. So this is, you see that phi inverse of alpha, phi inverse x is This is equal to Z. Now, psi of phi inverse of alpha equal to psi of Z, which is equal to beta. Therefore, what you have? You have psi composition phi inverse maps alpha to beta. Okay. So the image alpha and image beta are connected through this relation, namely psi of this is the connection. It's quite easy to understand. Now you can say that psi is an isomorphism, therefore psi inverse is an isomorphism. So also phi inverse or so also phi and phi inverse are both isomorphisms. Okay. Now you see that starting with alpha, you have a unique path that will take you to beta. What you do? Pick some element here. You can construct the set. How do you construct the set? The z is going to be, if alpha is alpha 1, alpha 2, etc., alpha n, then the z is taken as alpha 1 x1 plus alpha 2 x2 plus etc. alpha n xn. So you have an element in Rn. Now psi is defined on this. Apply that. So you rewrite that z in terms of y1, y2, etc., yn, which will fix the beta 1, beta 2, etc., beta n, and therefore the beta, therefore the image of alpha and beta, the image of beta is obtained. Now this is the connection that you have. So essentially these two maps, these 2 points are connected by psi composition phi inverse. Now you see that psi composition phi inverse is an example. It's an example. Okay, fine. So that gives the way to go about to change the coordinates. So it will give a psi composition phi inverse will give you an isomorphism on Rn. Okay, which corresponds to the change of coordinates from x1, x2, etc., xn to y1, y2, etc., y. Okay. So this is how the 2 things are connected. Now what we are interested in is getting some more transparency on this. Okay. So before that, I would probably indulge on an example and do some calculations so that you will know what we are going to do. So example. We take R. I don't want to complicate things. All the features are there when you work on R. Okay. We have a copy of R2. Then on which we choose a vector x1 x2. That means we already have the meaning of this is your x. This is equal to x1 v1 plus x2. So our reference, basic reference system is E1, E2. Now what do we do? We work on an isomorphism. What we do is we choose now a ordered basis. Okay, so that's how we did it. We chosen an ordered basis to fix an isomorphism. So we consider, observe that one minus one, one is an so basis on R2, we choose an ordered basis. Now let us compute the isomorphism corresponding to that. What is the isomorphism that you have? So we want to see the image of x1, x2 under this, the map determined by phi. So let's so how x1, x2 is represented in terms of a new basis. This is what we are looking at. Okay. So what you do, see x1, x2 equal to x1 into 1 0 plus. Now we compute 1 0 and 0 1 in terms of the new basis. So you can easily show that this, you verify that 1 0 is equal to half of half of 1 minus 1 plus 1. That is quite easy to work because you write 1 0 as alpha 1 times 1 minus 1 plus alpha 2 times 1 1, and then you compare you get two equations to determine alpha 1 and alpha 2. Because this is a basis, one can solve the two equations and get a unique solution. Okay, so what do you have? 1 0 is identified with 1 by 2, 1 by 2. This is the new identification that you have, or what you have is phi of or you have phi of 1 0. Similarly, you write compute phi of 0 1. Phi of 0 1 will turn out to be minus 1 by 2. 1 by 2. This is actually minus 1 by 2 into 1 minus 1 plus 1 by 2 into 1 1. Okay, you can verify that it gives you 0. Therefore, what do you get? Now write x1 x2 in terms of, so x1 x2 you write as x1 e1 plus x2 e2. Therefore phi of equal to x1 into phi of e1 plus x2 into phi of e2. Now what you do is, you know what phi of e1 is, phi of e2 is. Just substitute that and then find out. Okay. So what do you get? Okay, you can phi of x1 x2 can be written as so you see that x1 x2 equal to x1 e1 plus x2 e2, and this you can write as e1 and e2 we have already written. One zero, this is equal to x1 into half of 1 minus 1 plus x2 into minus half of 1 minus 1 half of 1. Now you can rewrite this in terms of 1 1 and 1 minus 1. Okay. So you see that this is equal to x1 minus x2 divided by 2 into this is it. So what do you get? So you see that phi of this is equal to the ordered pair this is it. Now you can easily check whether this is true, because phi of 1 0 that is put x2 equal to 0, so you get 1 by 2 1 by 2. If you take phi of 0 1, then you get minus 1 by 2 1 by 2. So that is the image. So we keep this. What about sine? So we make the similar calculation with sine. Okay. Oh, okay. We have not introduced it. Okay. So this is what you have. So x1, x2 under phi goes to the following vector. Now we make another choice of a basis. Let us choose another ordered basis for R2. Say 1, 2. Verify that this is a basis. Okay. You have to check that this is linearly independent. So, that's quite easy to do. So this is an ordered basis. We choose this ordered basis. Let psi be the isomorphism associated with this choice. Now, as before, you carry through this calculation. Okay, you can quickly work out. You will have to work out how 1, 0 is represented in terms of 1, 2 minus 2, 1. So you can have the following computations. Now you see that E1 is identified with, or psi of E1 is equal to 1 by 5 minus 2 by 5. Psi of E2 equal to 2 by 5 1 upon. These computations you carry through, and you can show that, compute that x1 E1, this is equal to x1 into 1 by 5 minus 2 by 5 minus 2 1. So also plus x2 into 2 by 5 1 2 plus 1 by 5 minus 2. So what we have done is to identify the representative. Okay. Then rewrite this in terms of this basis. If you rewrite this in terms of this basis, you get another copy of R2 here. You have psi here. Psi corresponds to the basis. So this phi corresponds to the basis 1 by 2, 1 1. So psi corresponds to the new basis that you have chosen, namely 1 2 minus 2 1. So psi minus 2 1. And here phi corresponds to the basis. What is the 1 minus 1 1? This is the choice that you make. Then you see that what is the image of x under the new, when you represent x in terms of the new basis. The corresponding point is going to be simply x1 plus see that so x1 e1, so x1 e1 plus x2 e2 will be simply x1 minus 2x2 by 5 1 2 plus minus 2x1 plus x2 divided by 5 into minus 2 1. Therefore, x is now mapped to the ordered pair minus 2x1 plus x2 by 5. This is the connection. So you have this minus 2x1 this is important. You can quickly check what happens when x1 equal to 1, x2 equal to 0. You get 1 by 5 minus 2 by 5 and 1 by 5 minus 2 by 5, and then psi of E2 equal to 2 by 5 1 by 5. So that is checked. Okay. So you have now the second result, namely psi of Okay, so we have got the images now, right? So these are the images. So what we are interested in actually finding out what exactly is this. We are interested in computing this map. Okay, right? So we will do that. Now here you see that you have certain advantages. Okay, right? What are the advantages? Again, let us look at both phi and psi. See, the point x1, x2 that you have chosen is a generic point. Okay. Therefore, if you represent x1, x2 as a column vector, then you see that this is mapped by something to minus x2 by 2 okay. You can quickly see what kind of map is it. So you can represent it by a 2 by 2 matrix. No moment's observation and your experience on working into matrices tell you that this is represented. This can be represented by a 2 by 2 matrix. So what is the 2 by 2 matrix that you have? You have half, then minus half, so that when you multiply this row with this column, you end up with this. And then you have got, therefore phi has a matrix representation, given by this square matrix 1 by 2 minus 1 by 2 1 by 2 1 by 2. We will formalize all these things later. Okay. I put a square bracket to see that this is the, so phi is identified with this. Likewise, psi also can be represented. Now you see that psi is identified with a 2 by 2 matrix through multiplication operation. So the action of phi on the vector corresponds to multiplication of the 2 by 2 matrix on the column vector x1, x2. So this turns out to be, it's quite easy to work it out, 1 by 5 2 by 5. Actually you go here, okay, 1 by 5 2 by 5 minus 2 by 5 and 1 by 5. The action is this. Minus 2 by 5, 1 by 5, this is the vector. So both are now represented by 2 by 2 matrices. matrices, and the matrix multiplication, if you reckon x1, x2 as a column vector in R2, then this can be thought of multiplying x1, x2 from the left by the 2 by 2 matrix, so that you get a column vector. So this is the transformation. Therefore, psi corresponds to the transformation. So this is actually, you are now putting everything in. In fact, when we try to write down representations of linear transformations, you will see this. So what you are having now is this. You have L on R2 can be identified with, say, M. This is a matrix of 2 rows and 2 columns on R2. Okay, right? This is a linear transformation on this. Okay, so what you have is that T is identified with a 2 by 2 matrix T belonging to So what do you do? The operation is this. T x is identified with the column vector T acting over the vector x. The vector x is column where x is this is identified with this operation. Now you see that this identification is, you can show that later we will see this. See, this is an invertible. If T is invertible, then this matrix is also invertible, otherwise it is not. Okay. For instance, the specific things that we are considering right now, you see that phi is a linear transformation on R2. Psi is a linear transformation on R2. Both are isomorphisms. Therefore, they are invertible. Okay, the inverse exists and the inverses are also linear transformations. So, phi is identified with bracket phi. Psi is identified with bracket bracket psi. So this is the transformation, this is the linear transformation, these are the matrix representations of that, and they are precisely given in this context by this. So you know how to compute this. It's just giving a feel for things. Now you see that, okay, we will make a quick calculation to ensure that what we have done is along the right track. Okay, so what is, so you will see that phi inverse can be identified with the matrix for phi inverse, and so also about psi, that we don't need. Therefore, what is the one that you have? See, you see that the two things that connect the images are the following. You see that I will draw the picture again so that you have the diagram readily available to you to check. So let me write. Okay. Okay. So let me rework on the picture. So I have phi going to what is called phi x is what? Phi x is given by this is the point this coordinates are given. Now I have here 2x1 x1 plus x1 plus minus 2x1 plus x2 by 1. These are the points. So this is psi. Therefore, what is this map? This map we have already seen is denoted by phi inverse. Sorry. Yeah. Phi inverse. This is the map. This is the map. This is the map. Okay. This is identified. Okay. Therefore, now you should be able to write this map also in terms of a 2 by 2 matrix. What you do? What you are asking for is this. See, x1 minus x2 by 2, x1 plus x2 by 2 is mapped to x1 plus 2x2 by 5 and minus 2x1 x2 divided by 5. So this is done by possibly by the matrix of phi inverse psi composition inverse. This is what you are doing. So what is the matrix of that? Okay. So my claim is this. This is really true. We'll verify. Because the verification will give you some confidence in generalizing this. Okay, let us come to this. See, I think that you should put your hand on examples. Unless you put your hand on examples, you will not get a hang of what is going on. It's much easier to just look at a book and read something and then get a feeling that you have understood everything. And then when it comes to the precise working, you will find that there are a lot of codes. Okay? Therefore, let us start working on this. Now, my speculation is this. Psi composition this is equal to the matrix of psi into the matrix of phi inverse. Okay? Okay, what is the, see, we know the matrix of phi equal to, and this is equal to matrix of psi into matrix of inverse. Okay. So matrix of phi inverse, okay, the matrix of phi is what you have. What is the matrix that we have already written? It is equal to 1 by 2 minus 1 by 2, 1 by 2, 1 by 2. This is it. Now you verify that. This is equal to. Let's compute this. So you can show that this is exactly equal to 1, 1, minus 1, 1. So you show that I mean, this you verify. Verify. Verify this. So that you are convinced that this is indeed the okay, let's do that. 1, 0, 0, 1. And the other way around. 1, 0, 0, 4. Okay. So that is verified. I mean, that is totally verified. Similarly, you observe that the matrix of this is equal to matrix of psi is equal to what? 1 by 5, 2 by 5, minus 2 by 5, 1 by. Okay, this is the matrix of psi. Okay. Now compute what? Compute psi inverse. This you can verify is essentially equal to 1 by 5, 2 by 5, minus 2 by 5, 1 by 5 into the matrix phi inverse, matrix of phi inverse 1, 1, minus 1, 1, which you can verify is essentially equal to minus 1 by 5. Check whether it is true. Minus 1 by 5, 3 by 5, then you get what you call this as minus 3 by 5 and minus 1 by 5. This is it. Okay. Now the next verification that you need is whether this is sent by to this. Okay. So check this is true. So compute this. Minus 1 by 5, 3 by 5, minus 3 by 5, minus 1 by 5, x1 minus x2 by 2, x1 plus x2 by 2, this is equal to, see whether you get this or not. Okay. Check whether you get this. That is x1 plus 2x2 by 5 minus 2x1 okay. So you verify this. I leave it you to verify this. Okay. Okay, right. Minus 1 by 5, 3 by 5, minus 3 by 5, minus 1 by 5 is equal to x1 minus x2 by 10, 3 x1 plus x2 by 10, and they add up to 2x1 so x1 by 5 plus 4x2 by 10 is, this is true. Similarly, this one you verify. I leave you to verify this. Therefore, we have made sure that all our computations do work according to the general theory that we have developed. Okay, right? So this is a good example on which you have worked on this. Now I will just give a picture of the whole thing. What are the various bases that we are working on? Because you work with R2, this is standard basis. This is R. Now what is the, so this is E1, this is E1, E2. Now what you have done is two bases that we have chosen. One is of course 1 minus 1 and 1 1. So 1 minus 1, 1 minus 1 would be this is the second base and use a different color. This is one of the axes or coordinates that you use. And then you have 1 minus 1 and 1 1. 1 1 is of course this. So this is the coordinate axis. Okay, so this is 1. This is 1. One minus 1 and 1. So this is the new coordinate system that you have introduced. What is the third coordinate system that comes into play? The third coordinate system that comes into play is in fact 1 2 minus 2 1. So 1 2 is this one. This is 1 2. So you have a vector here, and then you stretch this to get the coordinate axis. Then you have 1 2 and minus 2 1. This is minus 2. Okay. Minus 2 is minus 1. This is minus 2 and 1 is this. So this is the axis. Incidentally, I have chosen all these coordinate systems as orthogonal coordinate system, but that is not necessary. Okay. The important factor is that 1 0 and 0 1 is a linearly independent set of vectors. So also the pair 1 minus 1 and 1 1, that is also a pair of linearly independent vectors. So also 1 2 and minus 2 1. So this is minus 2. This is 1 0. Minus 2 1. These are again linearly independent vectors, but it so happened that my choice made it orthogonal. It's not necessary. It's just probably helps you in some computation, if at all in the general scenario, but otherwise it is immaterial. Okay. So what we are planning to do next is to generalize this. Okay. In the general scenario of RN, how all these computations do look like. Now I feel that you should construct your own examples and then duplicate this analysis after understanding it properly. Because if you do that, you will get a feel and you will also get a confidence. Okay? So now you see that with all these figures that I have drawn there, you will get an idea. So you are using, this is our standard coordinate system. This is a new coordinate system that we have introduced. This is a third coordinate system that we have introduced. So all the three coordinate systems are as good as any other. In fact, any pair of vectors which are linearly independent in R2 will serve as a credible coordinate system. Okay? So with these comments I stop here, but now you start working on these ideas. So in between I should also say that, see, we have been abstractly looking at the maths phi inverse, then sine inverse, and so on, and you see that, and there is the inverse map of phi inverse, and we were asking what is probably the matrix representation, because we found that any such map can be any linear map. So that's what we are going to do. Any linear map can be identified with a corresponding NFI matrix, inducing a ordered basis. Now here you have seen that when you introduce different bases, okay, this yellow basis or the orange basis or the white basis. In the white basis you started with x1, x2. In the yellow basis the same point will have a different coordinates written in terms of x1 and x2. In the orange basis you have the same point represented by a different coordinates. That's the important thing. So the coordinate system essentially fixes the coordinates. So the same point will be having different coordinates in this. Now all this can be easily understood as mappings from R2 to R2. This is what we have done. Okay, and then we have also just glossed over this idea that the matrix representation of phi and the matrix representation of phi inverse are connected by the inverse of the matrix of phi. The matrix of phi inverse is equal to the matrix of phi. Inverse. This we have just assumed. Now you will have to, in fact, make sure that this is indeed right, because rest of the calculations do depend on that. Okay, so these are the little things that you have to verify, but in the general scenario we will explore this further. Okay, right? Therefore, any type of, in fact, you see that whether this exists or not, this exists because you see that the basis that you choose, these are linearly independent vectors. The white ones are linearly independent vectors. The yellow ones are linearly independent vectors. The orange ones are also linearly independent vectors. So going from one system into the other will, or the corresponding isomorphisms will be always invertible isomorphisms, and their matrices are also linearly, if you look at carefully what are the components of phi, find out this phi, find out what this stands for, what psi stands for. What does phi stand for? Phi is given by the matrix half, minus half, then half. When you see that two rows are linearly independent, and how are they related? How are these related? So this is actually half of x1. So x1, x2 goes over to half of x1 minus half of x2. So that comes in. Similarly, this is half of x1 plus half of x2. So I just got this. So this is equal to, see, half of x1 minus half of x2 and half of x1 plus half of x2. You see that this half minus half appears here and half appears here. Okay, so this is the connection that you get. Sorry, this is I'm afraid this is sorry. The corresponding one is this. Let me start this. Okay. So half. What do you get? Okay, so there is a connection between these images also, the vectors that you get. Okay, so we have a certain computation which gives you what? Phi of 1 0 is what? Phi of 1 0 is half. Is phi of 0 1 is equal to minus half. This is what phi of 1 0 is 1 half. Phi of 0 1 is equal to minus half. So what happens is this part, this will come out as the column vector here, and this will come as the column vector, the second column vector here. So that's an observation that we make, and we will see whether this observation is really true or not. Okay? So that's the observation that we make. Okay, I think I will stop here today's lecture, and then we will try to generalize this in the next lecture. So it will be really work and explore. In fact, most of this will in some form or other will help you when you start dealing with the nonlinear functions. So thank you very much.